Hello, everybody, and welcome to another episode of TWIML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. The recording you're about to hear is the first of a handful of interviews I was fortunate enough to be able to record live in New York City from the O'Reilly AI and Strata conferences that I attended last week. I'll be sharing these interviews on the podcast over the next several weeks, and I think you'll really enjoy them. I'm especially excited to lead off this series with an interview with Carlos Guestrin. Now, if that name sounds familiar, it's because I've discussed Carlos's work on the show a number of times, most recently when I discussed Apple's acquisition of his company Turi back in August. In addition to Carlos's new role at Apple, he's also the Amazon Professor of Machine Learning at the University of Washington. Earlier this year, Carlos, along with one of his PhD students, Marco Ribeiro, and postdoc Samir Singh, published some very interesting research into the explainability of machine learning algorithms. My conversation with Carlos is focused on this research and the paper that the group recently published called Why Should I Trust You? Explaining the Predictions of Any Classifier. This paper has been on my reading list for a while, and I encourage you to take a look at it. Of course, you'll find links to Carlos and the paper in the show notes, which you can find at twimlai.com/talk/7. A quick note about the background noise in this and the other on-site recordings. They're not too bad considering the noisy caverns in which they were recorded, but some of you might find the murmurs and bumps a bit annoying. If you find yourself in this camp, please accept my apologies. And now, on to the show. So hey everyone, I'm here at the Strata conference in New York City, and I happen to find Carlos Guestrin, who we've talked about on the podcast before. He's the Amazon Professor of Machine Learning at the University of Washington, and we've known each other for a bit. So, Carlos, say hi.
Hi, thanks for having me here. And it was great running into you. It's a great event.
Yeah, absolutely. In fact, I think we probably had a briefing like right at this very table a year or two ago.
Yeah. we and I think we met at this event in this very place.
Right.
There's that room over there.
Yeah. So I guess I'll say very briefly to the audience, we're not in the most convenient spot for podcasting, so if there's the occasional trolley rolling by, just try to block that out.
And if you want some lunch, it's right behind us.
Right. But I'm sure you'll won't remember that at all because we're going to have a great conversation here. First of all, congratulations. On the acquisition of Turi, Dado, Graph Lab by Apple. I mean, that was amazing.
Yeah, we're very excited to work with Apple. It's great.
Awesome. So why don't we just start with introductions? Like, introduce yourself, talk a little bit about your background. I think a lot of people kind of know what you've been up to, but
sure, I'm happy to share. So. I'm Carlos Guestrin. Been working in machine learning for a long time. So I was a professor at Carnegie Mellon for about 8 years, and then at University of Washington since about 2012. And been excited about machine learning for a long time, and worked on many areas of machine learning. Most recently, a couple areas have been exciting to me, really around dealing with big data and the two sides of that. So on one side, algorithms for machine learning that scale to very large data sets. So how can you scale up to deal with tons of data? And the second side is what I think about as the human side of machine learning. So how can a human understand large data sets? How can a human understand what machine learning algorithm is doing? And bringing some kind of human perspective into the mix. So I think about those two sides, the computer perspective and the human perspective of machine learning in large data sets.
And I imagine there's also a fair amount of overlap and intersect between those two.
And of course, right? So the bigger your data, in a sense, the harder it is to figure out how to make it work, but it's also hard to figure out what's going wrong with that. So debugging a machine learning algorithm that requires you to run in a cluster with tons of machines is just almost an impossible task. And honestly, the way I think about it is that there's no machine learning without humans in the loop.
Right.
We're trying to build this incredibly intelligent applications that are going to be self-sufficient, but we'll always have humans be part of the process at some point. And so making that more human is a very important part of machine learning. It's been understudied in my field, but it's something that I'm very excited to engage in as well.
Yeah. So there's humans in the loop in lots of places, actually, and one of the places that humans are most certainly in the loop is, on the back end of a machine learning recommendation. Right. And your group has done a lot of interesting work very recently, at least, on explainability. Can you talk a little bit about how you arrived at that research area?
Yeah. So just in one sentence, we're interested in being able to provide more transparency to machine learning, be able to explain why a machine learning model makes a particular prediction or why it behaves a certain way. Now, we fell into this topic kind of interestingly in various ways. So, for example, in academia, we're working with various folks in application domains, and we said, come use machine learning, solve this problem, it's going to be awesome, we're going to change your life. And their response was like, sounds great, but why should I trust this model?
Right.
What is it doing?
Right.
And I was like, it's got great accuracy. So that's one side.
That's somehow unsatisfying.
It's unsatisfying. No, it's not enough. It's really not enough.
Yeah.
We can talk about why it's not enough. And then on the other side, once we build a company around machine learning, Turi, Dato, GraphLab, as you mentioned, we started working for a lot of companies that brought machine learning to production, and there was always a step that nobody talked about, but it was very fundamental. You train the model to do something, recommendations or whatever, predict churn, predict fraud.
Right.
And you want to deploy it as a service that every time you swipe your credit card, it makes a prediction about fraud.
Right.
You don't just make that happen out of the box. You want to make sure that model is working well and is doing things for the right reason, because if it's not, you're going to get fired.
Right.
And so you really want to understand why that thing is behaving the way it is. So by talking to
folks... And
not
just that, we've talked about on the podcast before, in Europe, there's legislation that's coming down the line that mandates explainability for machine learning and predictive applications.
Yes, there's legislation in Europe. And not just that, even in the U.S., for certain application domains in the financial sector, they mandate certain models you're allowed to use versus others, because they believe those models to be more interpretable or more believable or something.
Okay.
And so for certain tasks in that sector, you have to use a particular kind of model.
Okay.
It's and that just blocks a lot of the high accuracy models you might want to use. So it is a real issue. And I think that issue gets bubbled up in three areas. So one is just kind of general user of a model. How can they gain trust that service is doing things for the right reason? So if I go to, say, movie content recommendations, say Netflix, I want to know that I got recommended Lord of the Rings because I also like Star Wars. Mm-hmm. That gives me a sense that thing is doing the right things, recommending things that make sense to me, and they can begin to gain a relationship of trust with that artificial intelligence system underneath. Mm-hmm. So that's a kind of a more personal, consumery thing. But if you think about from, say, a decision that's really important and really life-changing, like a doctor making a decision about the treatment of a patient.
Right.
There, you want transparency. So if you have a system that says the patient is going to have cancer with 90% probability, most doctors are going to ignore that system because they might not trust it, and also because there's a holistic approach to medicine that we want to have where it's not enough to just make that one prediction. But if the system were to say, this patient is likely to have cancer because if you look at their MRI results, you see this lump, and if you look at this related cases, they were diagnosed in the same way. Right. And if you look at this latest study, this all corroborates the evidence, then I can gain a more holistic view and I can gain trust in the system. So that's the second piece. It's kind of gaining deeper insights as to what's happening in that prediction. Mm-hmm. And the third way, which is more kind of personal for me, is as a data scientist, I want to be able to make the models always better. And I want to understand when it's working, what's not working, so that I can improve it. And so Those are three areas: public perception of machine learning, making more informed decisions, not just a prediction for machine learning, and improving the models through feedback. And so transparency and explanation are going to be indispensable to make that happen. And unfortunately, as a field, we haven't invested enough in that topic.
Right, right.
Yeah.
But you guys have started to invest in this, and was it a month or two ago you published a paper that...
Yeah, the paper came out a couple months ago. And it's a system called Lime that my student Marco Ribeiro and postdoc Samir Singh wrote. Samir is now a professor at UC Irvine.
Okay.
And we wrote this paper based on the feedback that we're hearing and the need to do something more in this area. And there have been some other works in the kind of explainability machine learning, but what was unique about the perspective that Marco and Samir brought into the world is how they approach the problem. So a lot of the work in machine learning has been about finding models that are transparent or explainable, like we talked about in the financial sector. So these models have to be simple so that somebody can understand it. But the problem with that is that simple models tend to be inaccurate.
Right.
And so you're compromising accuracy for explainability.
Right.
And that's,
I
think, is a wrong compromise to have.
In fact, when you were making the comment, drawing the analogy with Netflix earlier, I was thinking to myself, I'd actually kind of rather that Netflix recommends movies that I want to see and not tell me how it got that, than recommend movies that I kind of don't really like and says this is the reason.
Yeah. So right.
So accuracy is still important.
But for me, the way I'm thinking about it is accuracy is number one.
Right.
You want to have high accuracy for the right reasons. But that's the main thing. Otherwise, you're not going to be able to solve the image processing tasks that we're seeing solved really well with deep learning today.
Yeah.
If you don't have the most accurate models. If I'm only allowed to use a very simple model, like a shallow decision tree, you're never going to be able to detect objects in an image.
Right.
So what's the point?
Right.
We're not going to build that kind of artificial intelligence system. So what we did was say, okay, let's take accuracy as a requirement.
Right.
And so that means that we want to be able to give a data scientist the flexibility to choose any model they want.
Yep.
And the question is, can we provide an approach that can explain the prediction for any model?
Right.
That was like the question. And I think it's a really beautiful question. And, the way that the work came together was really interesting. Of course, it's only scratching the surface of the possibility. Right. But what basically Marcus Samir did was come up with a system that says, okay, I want to explain a particular prediction. Why did you like that movie? Or why does this patient have cancer?
Okay.
And the way we're going to explain it is in a simple way that's good just for this prediction. And we're going to do it by highlighting the pieces of the input that we believe the model was most important for the model to make this decision.
Right.
So for the doctor's example, it is this particular area of the MRI, this particular studies that are going on, these related cases. So that's kind of small explanation. For the recommendation system in Netflix that you're unhappy with, it might be that the underlying system is very complex and very accurate, but the explanation we have to give you is kind of very simple, but somehow has to be faithful.
Right.
It has to say, it behaves like the model for this particular prediction. It's not like the model only uses,
Sure.
Lord of the Rings for everything, but for this prediction, that's what mattered.
Right.
And so that's how we went about doing it. And, we did a bunch of user studies that really showed that this can be very powerful and can be used in various ways. So it's pretty cool.
What was the nature of the user studies?
So one of the really cool user studies that Marco designed, let me just step back and say, it's really hard to evaluate explanations because it's a subjective thing, right? So how do you even figure out it's doing anything interesting? And so Marco,
and maybe if it's better, I want to get into kind of how it works and what the research actually showed. If it's better to do that first, we can do that first and then circle back to the user studies.
It is you're the boss. Yeah. So let's talk about how it work. Let's start from there. So the way it works is to say, I want to have a particular there's a particular prediction. I want to explain why it was made. Why did the model make that prediction the same way? And the way we're going to explain it is, let's look at the behavior of the system, the behavior of this complex model around this prediction. So not everywhere, but around it. Okay. So for this particular patient, I'm going to try to explain why the model thought it had cancer. So let's look at patients around it, some that were predicted to have cancer by the model, some that were not predicted to have cancer by the model, and fit a simple explanation that explains the difference between those similar patients. It doesn't explain the difference between every patient, but just patients that kind of like you. So patients that had most of the same characteristics as you that have cancer had these things going on, and patients that have similar characteristics as you that don't have cancer had these other things going on. And that gives me a lot of insights for this particular decision. And that's how, more or less how it works.
So as a coarse approximation of what I'm hearing, take the example of that you use in your course, predicting real estate prices based on a bunch of different variables. It almost sounds like, you might have a model that's a regression model that's predicting based on house size, right? And the Lyme system is almost a reverse regression that's going the other way, like predicting what the inputs might be based on the output. Is that
in a sense?
So
one way to think about it is house prices are very complex. It depends on the neighborhood you live in, the characteristics of the house, everything around it. So there isn't a simple explanation why your house costs $5 million, right? That's how much your house costs. And so,
thanks. Can you give me a raise too, so I can pay for my $5 million house?
I'll double what I pay you right now. Why did your house cost $5 million? Why did the house cost a certain amount? Who knows? Really complex. The models can be very complex.
Right.
But your specific house, can I explain why the model predicted cost $5 million? That's very doable. I can look at your house, and I look at similar houses that were like it, and I can fit locally a simple model with only a few variables that were most important that's basically, let's say, linear. And it says, around your house, the variables that were most important were square footage and zip code and number of bathrooms. And that's really important for $5 million house. For a $500,000 house, it might be a different thing is more important. And so that's the kind of thing that the model will say. Right. So that's kind of how it works. It provides the key pieces of the input that were most distinctive for a particular prediction. And as I said, this is one way to do explanations. We're scratching the surface. There's all sorts of other ways you can imagine doing it, and I think there's a lot of opportunity to do even more. But one of the challenges is how do you figure out if this makes any sense whatsoever? If these kinds of explanations are good, if the algorithm is working at all. Like, there's so many dimensions that this can go wrong. How can you even figure out if this is at all reasonable, right? And Marco, Samir, and I spent a lot of time banging our head against the wall to figure out how can we even test this? How can we even measure it?
How do you explain your explanations?
How do you explain my explanations? And Marco had a couple of brilliant ideas that really surprised me. And so let me give you one of them. So he wanted to know if explanations are good and intuitive, that would mean that somebody who is not a machine learning expert, a layperson, could look at it and make good decisions from it.
Okay.
So that's what he thought. So how can we test that hypothesis? So he did two tests that validated that hypothesis in a really brilliant way. So the first one was...
If I can interrupt you, it sounds like that the aim of the research was not just to spit out like an ordered list of features in terms of weighting or importance in the output, but more generating a human readable description. Am I reading too much into this, or is that correct?
No. It was a human interpretable description.
Human interpretable,
not necessarily readable.
Okay,
that's one way to explanations can be many things.
Right.
We explored the human readable explanations, we the visualizations, we explored different ways to explain things.
Okay.
So here's the experiment that he did, which was pretty brilliant. So he took a data set and just a little background, which is kind of a fun story that I just told. There's this famous data set called the 20 news groups data set.
The what?
20 news groups data set.
20 news groups? Okay.
Yeah, it's a data set that's been around for about 30 years in the machine learning community.
Okay.
And It's from news groups, which you might not know what they are, but they were something that later called forums, now called Facebook pages, right? Where they have a topic and people talk about the topic and they post things.
Right.
And the data set was famous because the idea was, given the text of the posting, can you predict whether this was about Christianity or atheism or hockey or computers or whatever the topic was. And basically any modern machine learning approach gets 94% accuracy. So everybody used this data set in their classes. Like I used in my class and said, oh, machine learning is so cool, it gets 94% accuracy. When Marco ran his explanations on it, it turns out that the main features being used are things like the email address of the poster.
Okay.
Like, so sam@gmail.com always posts in the, I don't know what your interests are, Sam, but in the, let's say, podcast news group.
Rec.podcasting?
Yeah, rec.podcasting, clearly. And obviously it's a great predictor.
Right.
But it doesn't generalize to somebody else.
Right.
And so it's not a good feature. It's a good feature for you, but not a good feature for the world.
Right.
And so if you remove those kinds of features, the accuracy went down from 94% to only 57%.
Yeah.
So this data set that everybody has used for decades, machine learning so well, actually wasn't doing so well.
Wow.
And you were able to see that from the
That's pretty
explanations. So the question that he wants to ask, going back to the user study, was, as an expert, he discovered this with the explanation. Can somebody who's not a machine learning expert discover this and improve the performance of a machine learning system?
Yeah.
So he took this data set and he was only getting 57% accuracy, and then cleaned the data as much as he scrubbed, remove all these bad features, and retrain the model, and he was able to get about 70% accuracy.
Okay.
By removing all the bad features like sam@gmail.com.
And then coming up with a new model, or
new model trained on that
clean data set. Okay.
So that's the gold standard, clean data, and there was the dirty data.
Yep.
And the question was, using explanations, could mechanical Turkers who know nothing about machine learning identify bad features? We said, look at the explanation, just cross out things that you think should be relevant for this decision.
Oh, interesting. Okay.
We didn't say anything else, just cross out things that you think are irrelevant. And we thought, okay, could crossing it out get performance so close to Marco's gold standard from non-experts?
Meaning, so you ran the LIME system, the explanation system, against the dirty data set.
Yeah.
You came up with these explanations that included things like emails that should be irrelevant, and you asked Turkers if they could figure that out.
Figure out what parts of the explanation,
right?
What, in a sense, what features you thought should not have been used as part of this decision.
And how did that go?
So, after just 3 rounds of mechanical Turkers crossing things out, they were able to get better accuracy than Marco's gold standard data set.
Wow.
So they were able to clean the data better than Marco did.
What is a round in this case?
A round was showing the... So I didn't go into details, but we showed the explanations to a number of mechanical Turkers.
Yep.
They were able to cross it out and retrain the model.
Okay.
Then we showed the new model to different set of mechanical Turkers. They crossed some things out, and we showed it again. So we just did that 3 times, 3 iterations with non-experts. And by looking at explanations, they were able to find all sorts of problems in data, clean it, and get better performance than Marco did, like sitting down and like trying to clean the data himself.
Wow. Which
is surprising. So that means that non-experts, this is just an example, so just the non-experts are able to understand explanations of a complex machine learning system and provide some feedback to that system that can be used to improve the performance of that system, which was really surprising.
Wow. That's very cool.
It was very cool. And then the second user study, so then, Marco was bold and then wanted to come up with an even more interesting bold study.
Go, Marco.
And the second one was also really exciting. So here's what he wanted to ask. When you train a machine learning model, you usually train it on some data and you evaluate it on some data that you hold out. It's called the test set.
Sure.
So that you don't get a biased prediction of how well the model will do. So you can imagine some models might do well on the training set, but don't do well on the test data set, so we want to throw out those models.
Yep.
And some models will do well on the test data set, and and then you want to keep those models. So that's what you typically do. If you go back to the 20 news groups data set, if we had just looked at the 20 news groups with the email addresses in the test set, you do well in the test set, so you think you're doing well.
But it wouldn't validate very well.
It wouldn't validate very well.
Right.
But if you had tested on some other data set that didn't have Sam at gmail.com, then he would have done badly, then he would be able to throw it out.
Yeah.
So here's the experiment that Marco did, which I thought was brilliant. He split the data into a training set and a test set.
Right.
And he trained a bunch of models, a lot of models on different random subsets of that input data, of the training data.
Yep.
And some models did well on the training data, and some models did badly on the training data.
Okay.
He threw out everything that did badly on the training data because we only want to keep high accuracy models.
Okay.
So he kept only things that were accurate on the training data.
Right.
And then he looked at the test data set, and some models did well on the test data set, and some models did badly on the test data set.
Right.
And then he said, the models...
And up till now, I mean, this is pretty standard what any data scientist would do. And,
yeah. Pretty standard.
Run a bunch of models, see what sticks against the wall. And,
yeah, exactly.
Yeah.
Now he did the following.
Okay.
He took mechanical Turkers who know nothing about machine learning.
Yep.
And showed them explanations for the models that did... They didn't say anything about hit process, and it was all randomized and blind and everything, right?
Right.
So the explanations for models that were doing well on the test set,
Yep.
and models that did badly on the test set.
Okay.
And they both look equally good on the training set.
Yeah.
And I forget.
By
like
test
about,
set, you mean the validation.
Actually, was a hidden. In this case, it was a hidden test set. But you can think about a validation. It was a hidden test set. So it was something that you wouldn't do as a data scientist. But
right.
In the sense
he held off some additional data and he ran both of them.
He held some additional data. He ran lots of models that did well on the training set, and he picked out some that did badly on the test set and did well on the test set. Mm-hmm. And then showed explanations for all those models to mechanical Turkers and asked, which model do you think is going to be better in the real world based on the explanations of why they're making the predictions?
Yeah. And they were asked to pick between two?
Yeah, between two.
And you were comparing them with a coin flip, right? So
yeah, compared to
and they did better than a coin flip?
So a coin flip gets 50% accuracy,
right.
87% accuracy.
Wow. So totally untrained, the unwashed mechanical Turk masses are basically creating, doing feature engineering on models in their heads.
So the first part was feature engineering. The second part, it was like model selection, basically.
Right.
They were able to look at explanations and figure out this model is stupid.
Yeah.
Even though on the training set, it looked great.
Yeah.
But in the real world, it's going to be bad.
Wow, that's pretty amazing.
And that was amazing to me. And the fact that... we can do that. As I said, we're only scratching the surface here, but the fact we can do that, to me, says humans will be in the loop in the long run.
Right.
There are insights to having humans in the loop, because even kind of the statistical problems that underlie this question, like if we discuss for a long time, we can talk about why this is relevant statistically. Yeah. Humans might be able to pick those out. And they'll be able to do better feature engineering. They'll be able to understand problems they're going in the data, even untrained folks. And now, if you imagine doing this to get more insight for doctors or for systems in the real world, I think you could do really amazing things. So it's pretty exciting to me to start, exploring this further and further. That's
very cool. Let me ask you this. This is kind of an in-the-weeds question, but were the features what you might think of as natural features or engineered features?
Yeah, so that's the really interesting or a really interesting question. So the underlying models use the engineered features. So for example, he also showed this was good for deep learning models for images, which use really learn complex features of the data. But the way that he explained was from pieces of the input. So the assumption that he made was the input is interpretable.
Okay.
And by selecting pieces of images or part of the text, a human can look at that and say, oh, this makes sense. If we looked at like the seventh layer of a neural network and say, oh, this is a human would be like, what is that?
Yeah.
And why do I care? You know? And so that's why we bias towards this approach. It doesn't mean that in the long run we want to invent something better that looks at the features, because the problem might be down in the features, it might be down in the weeds. And that's kind of where the research should go. But as a first step, we looked at pieces of the input.
And
basically.
it's totally model independent?
It's
like
totally
you could work on
we call it model
neural
agnostic.
network models?
Yeah. We've done this with deep neural networks. We've done this with boosted decision trees. We've done this with lots of different kinds of models.
Wow. So I know we need to get you off to your next session. Where can folks learn more about this?
So if you just search for my name in Lime, you'll find our paper. It was a KDD this year.
Lime, L-I-M-E?
L-I-M-E.
Okay.
You can also find a GitHub project that Marco has been putting together. We've open sourced some of these ideas. But yeah, it's been a pretty exciting work, and you just keep tracking. Marco, Samir. There'll be a lot more in the pipeline. This is a really cool thing.
That's awesome. That's great.
Yeah.
And if folks want to reach out to you, you're on Twitter, or what's the best way to get in touch with you?
I'm on Twitter, Guestrin. It's my last name. It's the handle. And so reach out, give me some feedback. We're also, as you know, on Coursera teaching machine learning, and that's another place that I interact with folks.
Yep, and it's a great course. I highly recommend it. Very case study focused. Really enjoyed it.
Okay, thanks.
Great. All right, thanks so much,
thanks
Carlos.
For your time, man.
Yep.
I'll do a handshake here on the audio. Thanks.
All right, everyone, that's it for today's show. Thank you so much for listening and for your continued support. A quick story. If you follow me on Twitter, you know that I recently called out an iTunes review that I'm actually particularly proud of. In this review, a user that originally rated the podcast a 2 out of 5 based on their disappointment with the switch to the interview format came back and revised that review to a 4, noting that the interviews were getting better and that the format was really starting to grow on him. Now, don't get me wrong, please. I really appreciate those of you that left 5-star reviews on iTunes, and I hope the rest of you go run and do that right now. But it also felt great to see that in spite of his initial misgivings, the shows just kept getting better and the user eventually came around. That kind of feedback is great to read. Thanks to everyone who stuck with the show through the transition, and I hope you're continuing to learn a ton. Please join the conversation by commenting on the show notes at the TWIMLAI.com website or by reaching out to me on Twitter, where you can find me at Sam Charrington or at TWIMLAI. All right, everyone. Thanks again for listening, and catch you next time.